Hello everyone. In the second lecture of thermodynamics, our today's subtopics that are going to be discussed are thermodynamic equilibrium state, types of equilibrium, steady state, state function, perfect differential, and cyclic rule. So in this context, let's begin with thermodynamic equilibrium state. So a system is said to be at thermodynamic equilibrium state if, firstly, the macroscopic properties do not change with time. What are the examples of macroscopic properties? The examples of macroscopic properties are temperature, pressure, density, etc. So if these things do not change with time, then the system is said to have thermodynamic equilibrium state. Secondly, the system should be at rest without assistance of any external agency. What does it mean? Suppose, as for example, take the example of a tank of water. Okay, so in the tank, the water level remains fixed if there is no leakage at any part of the tank. So that level of water is at equilibrium. And why it is at equilibrium? Because the level is at rest, it is not changing, and you are not at all applying any kind of external force. That means you are not assisting the system by any kind of external agency. So the system should be at rest without the assistance of any external agency. And finally, each part of the system is undergoing mechanical equilibrium, thermal equilibrium, and chemical equilibrium. What is meant by mechanical equilibrium? If there is no change in pressure, that means delta P is 0. What is thermal equilibrium? If there is no change in temperature, that means delta T equals to 0. And what about chemical equilibrium? If the overall chemical potential remains the same at each part of the systems, that means each component does not change. The amount of each component does not change. That means the chemical potential of each component do not change. So delta mu equals to 0. So this part mu is little bit unknown to you. This part will definitely be discussed in your in the next part of your this thermodynamic lecture. So if these three types of equilibrium are established in each part of the system, then the system is said to be at thermodynamic equilibrium state. Now, classification of equilibrium. So equilibria are of three types, such as stable equilibrium, unstable equilibrium, and metastable equilibrium. Firstly, let's discuss stable equilibrium. You can compare stable equilibrium with this picture. Suppose this is a hole and the ball is taking the bottom position of the hole where it is at a stable equilibrium. If you try to move the ball by applying some force or constraint, then it will change its position initially, but it will come back to its initial position when this force is removed. So this type of equilibrium, it is a very stable thing. It's a very stable position where it is not possible to displace or dislodge this ball from this position. So this is a kind of stable equilibrium. So what is how it can be described? It can be described as a system is said to be at stable equilibrium if displaced to a new state and released from the constraint. Constraint means the force causing displacement. Okay, it always returns to the original state. That means where it was initially. Now, unstable equilibrium. Unstable equilibrium can be compared with this picture, where the ball is placed on the top of a peak. Okay, so a little bit application of any kind of external force can destroy its original position, and it never returns back to that position again. So a system is said to be at unstable equilibrium if displaced to a new state and released from the constraint causing displacement. It never returns to its original state. So these two are stable and unstable equilibrium. But if the system is in between stable and unstable equilibrium, then it is called a metastable equilibrium, and it can be compared with this picture where the ball is placed in the middle of a surface which has a chair-like structure. Okay. In this position, application of small amount of force or constraint, the original state remains the same. That means it is moving towards the right hand side or towards the left hand side. When the force is removed, then it comes back to its original state. But if the extent of the force is greater or it is very large, then it can go to a new position and does not come back to its original state. So these are the metastable states. So what about this? It is a state between stable and unstable equilibrium. If the displacement is not too large, then it is stable equilibrium. But if the displacement is too large, then it is unstable equilibrium. So if it is not too large, then it is stable, and if it is too large, then it is unstable equilibrium. So what are the examples of such metastable equilibrium? We have two examples here. One is a supercooled liquid, another is supersaturated solution. In a supercooled liquid, if you add the crystal of that liquid, then the whole liquid crystallizes out. Okay. Or if you stir it with a glass rod, then it crystallizes out. That means this type of equilibria are not so stable. It is in between stable and unstable state. Another example is supersaturated solution. What is a supersaturated solution? A supersaturated solution is such a solution where the accommodation of the solute are more than its maximum capacity. That means it is more than the capacity of a saturated solution. So there is some extra solute dissolved in it. So this state is neither stable nor unstable. It's a metastable state, because if you just add some solid crystal in it, then the extra dissolved solute would crystallize out. So it will then become stable. Suppose unsaturated solution or a saturated solution is the example of a stable equilibrium, but a supersaturated solution is the example of a metastable equilibrium. Okay. Now move on to steady state. If the macroscopic properties remain unchanged with time and system is at rest with the assistance of external agent, then the system is said to be in a steady state or a stationary state. So steady state or stationary state, what about this? You are applying some external force, or you are assisting it by some external agency, and that moment both the macroscopic and microscopic properties are changing, but still it seems to be at rest. Okay, we have two examples here. Suppose a consecutive reaction, A reacts to form B and B reacts to form C. Now at some stage of the reaction, the concentration of B becomes constant. That means dB dt is 0. That means the rate of formation of B is equal to the rate of disappearance of B. Okay, so that state is the example of a steady state. Or in another example, suppose you take a tank of water. So if there is no leakage, then it is a stable equilibrium. But if there is a leakage and simultaneously you are just making up the level of water by a running tap, okay, that means you are applying some external agency to maintain the water level as if it remains the same. In that case also you can say that the water is at steady state. You can compare this with some other examples of your daily life. Suppose you are cycling, you are not falling on the ground, or if you are playing with a top, it's running but it's not falling on the ground. These states are also examples of steady state. Okay, that means some force is being applied on it, and as if it seems to be at rest, but it is not at rest. Two types of properties are there: macroscopic property and as well as microscopic property. So microscopic properties are always changing, both in steady state and equilibrium state. But if the macroscopic property does not change, then it is equilibrium, and if it changes, then it is steady state. But another condition for being at steady state, that the system should seem as if it is at rest, and you are taking the help of some external agency. So let's compare this with some steady state and equilibrium state. Here, comparison of steady state with equilibrium. Look, a steady state is dynamic in macroscopic level as well as in the microscopic level. That means, as I have said, both microscopic level and macroscopic level are dynamic here. Both are changing. Okay. But here one thing is not written here. The system seems to be at rest with the help of some external agency. Now look at the equilibrium state. While an equilibrium state is static in macroscopic level but dynamic in microscopic level. So that is the main point of difference. It is the macroscopic level, that means pressure, volume, temperature, all these things remain the same. Okay, and the molecules are not at all moving, and you are not taking the help of any kind of external agency. But the microscopic level is dynamic. That means if it is a gas, the gas is at rest, but the molecules are always not at rest. Molecules are always moving. So as for example, a closed gas jar at a certain temperature and pressure is at equilibrium. Okay, but in the microscopic level, the gas molecules are always undergoing translational movement. That means they are always undergoing some kinetic motion. So in the microscopic state or level, they are not at all at rest, but its pressure and temperature remains the same. That means their macroscopic level is static. Okay, it is not dynamic. But in case of steady state, what we have learned, that both macroscopic and microscopic properties or levels are dynamic, and the system is taking the help of some external agency. In that case, it is at steady state. Otherwise, it is at equilibrium. Now, moving on to the next part, the state function and perfect differential. Actually, the path dependent functions are state functions. That means it is it depends which way the operation is undergoing. Okay, which way the operation is undergoing means the system may change from state 1 to state 2. Now in between there is some state 3, or there is some state 4, and finally it goes to state 2. Okay, if the overall change of that particular property, thermodynamic property, definitely, if it does not depend whether it is taking the third path or fourth path, then it is said to be a state function. Otherwise, it is a path function. Okay, all the energy terms such as temperature, such as enthalpy, then internal energy, these are all state functions. Then also all the say volume, pressure, temperature, they are also state functions. Okay, because they do not depend upon the path. So let us see what are written here. The functions that are generally path independent, that is depends only upon initial and final stages. Okay, just carefully see this thing, the function. It may be volume, it may be temperature, it may be pressure, it may be energy terms, it may be entropy, whatever. If it depends upon only initial and final state of the system and not upon the path in between, then they are known as the state functions. Okay, so what are the examples of such functions? The examples are temperature, pressure, volume, internal energy, enthalpy, entropy, etc. Secondly, the differentiations are called, or their differentials are called the perfect differentials or exact differentials. So differential of a state function is generally known as perfect differential or exact differential. And thirdly, the examples, or on the other hand, the path dependent functions are called path functions, and the examples of path functions are heat and work. Okay, so heat, that is Q, and work, that is W, are examples of path dependent functions. Now, mathematical definition of a state function. So if psi is some state function, okay, which is a function of x and y, so that psi equal to fxy, that means psi is a function of x and y, then the mathematical conditions of d psi, that is differential of psi, to become a perfect differential. So if d psi is a perfect differential, then psi must be a state function. Okay, so the condition of psi to be a state function is actually the condition of d psi to be a perfect differential or exact differential. What is the condition of d psi to be a perfect or exact differential? There are two conditions. One is del 2 psi over del x del y must be equal to del 2 psi over del y del x, and the cyclic integration of d psi must be equal to 0. Okay, what is the meaning of this first mathematical condition? The meaning of the first mathematical condition, you are just operating the psi function twice by applying different functions. First time you are differentiating with respect to y, keeping x constant, and what the result you have obtained, that result is being differentiated with respect to x, keeping y constant. But the vice versa is undergoing here in the right hand side. So you are undergoing the second operation in a different path. First time you are differentiating with respect to x, keeping y constant. Second time you are differentiating the result with respect to y, keeping x constant. So the path is different now. So if both the operations producing the same result, then d psi is a perfect differential. That means psi is a state function. Another condition, mathematical condition, is that cyclic integration of d psi must be equal to 0. That means cyclic integration means, suppose there are two states, 1 and 2, then integration from 1 to 2 of d psi plus integration of 2 to 1 of d psi must be equal to 0. This is cyclic integration. Okay, now we move on to another mathematical relation. This is not related to state function or perfect differential. This is such a mathematical relation which can be applied throughout the chapter of thermodynamics. Okay, so if some function of x, y and z are 0 and x is dependent on y and z while y and z dependent on x and z, this is not a full stop, this is actually a comma, then number 1, del x del y at constant z must be equal to the reciprocal of del y del x at constant z. This is one of the mathematical relations which will be useful for us throughout the chapter. And secondly, this del x del y at constant z into del z del x at constant y into del y del z at constant x is equals to -1, or the overall thing plus 1 equals to 0. Okay, this is also known as the Euler's theorem or the cyclic rule. Okay, now this cyclic rule can be verified with some example, such as you know the ideal gas equation PV equals to nRT. So that means PV minus nRT equals to 0. So we can say that the function of P, comma V and T are 0, isn't it? So in that case, cyclic rule can be applied. So we have PV equals to nRT and PV minus nRT equals to 0. That means function of P, V and T are 0. Therefore, P is equal to nRT by V. Now let's differentiate P with respect to V, okay, at constant temperature. Then it produces the result nRT. Now T is constant, so we have to only differentiate 1 by V, and the result is minus 1 by V squared. So overall result is minus nRT by V squared. Now nRT is actually equals to PV. So putting the value PV in the place of nRT, we can get minus PV by V squared, and one V is cancelled with another one in the denominator, which results minus P by V. So this is the relationship number 1, where del P del Vt is equal to minus P by V. Secondly, we have to differentiate V with respect to T at constant pressure. So V equals to nRT by V. Now let's differentiate V with respect to T at constant pressure. So the result is similarly nR by T, P, nR by P, which is equation number 2. And thirdly, we have to differentiate T with respect to P at constant V. How? So take T, okay, and the other terms to the right hand side. So T means PV by nR, okay. Now if you differentiate PV by nR, then in that case V and R all are constant, because V is constant, N and R are already constants. So we have to only differentiate P with respect to P, which produces the result 1. That means this is actually V by nR. So this is equation number 3. So we have already obtained all the 3 results. What are the 3 results? In equation number 1, del P by del Vt. In equation number 2, del V by del Tp. And equation number 3, del T by del P V. So let's multiply them. Equation 1, 2 and 3. These 3 results are summarized here, okay. The first one yields minus P by V, the second one yields nR by P, and the third one yields V by nR. Let's multiply them. The multiplication gives minus 1. So the cyclic rule is verified here to be valid, okay. So and also it is proved for PV minus nRT equal to 0. And finally, at the end of this lecture, another important mathematical implication. This is also very important, which will be applied throughout the chapter. Suppose a quantity z is a function of 2 independent variables x and y, so that z equals to f x comma y. Then what is the expression of this? This is very important, very important. It will be applied throughout thermodynamics and application of thermodynamics also in the next semesters. So what is the value of dz? dz is the value, the rate of change in z with respect to x at constant y multiplied by tx, plus the rate of change in z with respect to y at constant x into dy, okay. So this is for infinitesimal change. That means where the changes are very small. But if it is finite, the changes are large, and or it may be called for finite changes. Then dz can be written as delta z, and dx is written as delta x, and dy is written as delta y. So this mathematical rule is very much important, which will be applied throughout this chapter of thermodynamics, okay. And last but not least, we have to prove that V, that is volume, is a state function. So let's start with 1 mole of an ideal gas equation, PV equal to RT, or V equals to RT by P. Now let's differentiate V with respect to temperature at constant pressure. That produces the result R by P, and its double differentiation with respect to P next time produces the result minus R by P squared. Now let's change its path of operation. First differentiate with pressure, then differentiate with temperature, okay. So on differentiating with respect to pressure, firstly it gives minus RT by P square, and on double differentiation with respect to t for the second time, it gives the result minus R by P square. So both results are same. So these two terms are same. That means V is a state function. That's all for today. Have a nice day. Thank you.